Hello everyone. Today we will going to see some practice questions from the chapter General Organic Chemistry. This is part 4. Let's start. Disclaimer which says the images used in our slide deck are for educational purposes only. We respect the intellectual property rights of original creators and owners of these images. If you are the owner of any images used in this deck and have any issues or concerns, please contact us at sathee@iitk.ac.in and we shall remove the images. So this is our index slide. Today we will going to see the practice questions from question number 22 to question number 28. Let's start with the question number 22. The most stable free radical is. Options are THCH2 CH2 free radical, MECH2 free radical, Me2CH free radical, or THCH free radical Me. You have 10 seconds to solve this question. After that, we will see the answer. Okay, let's see. The correct answer is option D, that is PHCH free radical Me. So the most stable free radical is secondary benzyl radicals, like the given option, which is the answer, due to the resonance property shown by the benzene ring. Right? Free radical is basically you can say you can have cation and anion, right? But in the free radical, the extra charge or the extra electron or is deficient or extra is present at the atom, right? That is known as free radical. Okay, so the most stable free radical is secondary benzyl radical from the given options, and due to the resonance property shown by the benzene ring, and thus the most stable free radical is THCH free radical Me. That is, the option is the correct answer. Okay, let's move on to the next question. Question number 23. Correct order of nucleophilicity is. So you have to tell the correct order of nucleophilicity. Nucleophilicity means you have listened about the word nucleophiles, right? So how much strong the nucleophile is known as its nucleophilicity. So we have given some nucleophiles and their order in the increasing order, and you have to tell which one order is the correct one. Options are fluoride ion, the most stable, then the OH negative, then NH2 negative, then CH3 negative, or NH2 negative, then CH3 negative, then OH negative, then F negative, or CH3 negative, F negative, then NH2 negative, then OH negative, or CH3 negative, then NH2 negative, then OH negative, then F negative. So you have 10 seconds to think about this question. After that, we will see the answer. Okay, let's see. The correct answer is option B, that is the most nucleophile, the most stable nucleophile is CH3 negative, then NH2 negative, then OH negative, and the least is F negative. So the nucleophilicity is inversely related to the electronegativity of atom bearing negative charge. So first of all, nucleophile are having negative charges. That means they can donate the electrons to the major ring, or to which they are going to connect or they are going to react. Okay, so nucleophiles are having negative charges. That means they have extra electrons to donate. They can easily donate electrons to the other chain or the atoms or molecules to stabilize them, right? And it is given, we use the concept here, that nucleophilicity of any nucleophile is inversely related to the electronegativity of atom during the negative charge. Okay, so any atom having negative charge, how strong its electronegativity will be is inversely related to the nucleophilicity of that atom. So as you can see, fluorine is the most electronegative atom from the halogens and from all the atoms, right? So because of the electronegativity is so high for the fluorine, the nucleophilicity for the fluorine is lowest because they are inversely related. And that is why the correct order for the nucleophilicity is the most for CH3 negative, then NH2 negative, then OH negative, and then fluoride negative. This is the correct order, and this D option is the correct answer. Okay, now let's move on to the next question. Question number 24. The correct order of increasing basicity of the given conjugate bases is, we have given some bases in the form of R double bond CH3. We have to tell the correct order for the increasing basicity of them. Okay, options are the most basic for NH2 negative, then R negative, then C negative triple bond CH, then RCOO negative, or the most basic for NH2 negative, then RCO negative, then C negative triple bond CH, then R negative, or the most basic for R negative, then C negative triple bond CH, then NH2 negative, then RCO negative, or most basic for R negative, then NH2 negative, then C negative triple bond CH, and then RCOO negative. So you have to find out the correct order for the increasing basicity of the conjugate bases given. You have 10 seconds to think about this question. After that, we will see the answer. Okay, let's see. So the correct answer is option D. That is, most basic is R negative, then NH2 negative, then C negative triple bond CH, then RCO negative, least basicity. So in carboxylate ion, you can see that RCOO negative, known as carboxylate ion. The negative charge is present on the oxygen, right? A most electronegative element here. In the whole structure of carboxylate ion, the oxygen is the most electronegativity, or is having most electronegativity, or the most electronegative atom is oxygen, and in which negative charge is present. Thus, it is resonance stabilized. So resonance will happen, like this negative charge will go here. For the balance, the double bond will go here on the oxygen, negative charge will on this oxygen. So negative charge shifted to this extra electrons on this oxygen shifted to the double bond, and the double bond present here shifted to the negative charge. So resonance is happening, and this is the reason for the stabilization. And in C negative triple bond CH, the carbon is sp hybridized, right? Triple bond is present. That means sp hybridization is present. So its electronegativity is much higher than the nitrogen. Okay. Now, what we will do in the NH2 negative, nitrogen is more electronegative than sp3 hybridized carbon atom. Okay, so thus the order of the stability of conjugate bases will be R negative, then NH2 negative, then C negative triple bond CH, then RCOO negative. So what we have done, we have just add the electronegativity of different conjugate bases. Like in the RCO negative, we have the most electronegative atom, oxygen, and having the negative charges, so it will be resonance stabilized. Then we have the sp hybridized carbon, or this conjugate base, which is more electronegative than the nitrogen. And then we have the sp3 hybridized carbon atom in the R negative group, which is less electronegative than the nitrogen in the NH2 negative. Okay, so this is the order for the stability of the conjugate bases, and higher is the stability of conjugate bases, lower will be the basic character, because for the basic character, they should react, right? They should react to some acid or a salt to make a proper molecule. And if their stability is higher, so their basic character will be lower. And hence, for the order of basic character, we just reverse this conjugate basis stability order. So we will get this final order, which is highest for R negative, then for NH2 negative, then for C negative triple bond CH, then for RCO negative. So this is the basicity order for the given conjugate basis, which is opposite of the stability of conjugate basis order, and thus the option is the correct answer. Okay, now let's move on to the next question. Question number 25. Among the following, the least stable resonance structure is. So we have given some resonance structures. Resonance structures are those structures in which we can interchange the charges and bonds to stabilize, to provide the stability to the carbon, to provide the stability to the molecule. You can say more stability. So options are, you have this structure in which nitrogen is directly attached to double bond oxygen, single bond oxygen negative, and it is having positive charge on itself, and it is directly attached to the CH2, CH2, CH, CH2, double bond CH2, right? And similarly, in the B option, we have nitrogen and double bond oxygen, single bond oxygen negative, positive charge of the nitrogen, directly connected to the CH2 negative, CH2 positive, CH double bond CH2. In C option, nitrogen connected to double bond oxygen, single bond oxygen negative, positive charge on itself, connected to the CH, then double bond CH, then single bond CH2 negative, then single bond CH3 positive. In the D option, we have nitrogen having positive charge connected to two oxygen negative by the single bonds and directly connected to the double bond CH, then single bond CH, then double bond CH, then single bond CH3. Right? So these are different resonance structure given in the option. You have to choose the least stable resonance structure. You have 10 seconds to think about this question. After that, we will see the answer. Okay, so let's see. The correct answer is option A, that is this structure. The least stable resonance structure is A option. Here, two positive charges present at the adjacent places. You can see on the nitrogen, and the nitrogen is directly attached to the carbon having positive charge. So two positive charges are adjacent to each other, like two positive charges are on the atoms which are adjacent to each other. It elevates the energy and thus lowers the stability, because due to the repulsion between the positive charges, energy will be increased, and due to the increase of energy, the stability will get lowers because they are inversely related, right? That's why the least stable resonance structure will be A option, and we have asked the least stable resonance structure, so the option is the correct answer. Okay, let's move on to the next question. Question number 26. Which of the following molecules is least resonance stabilized? Again, the same question. We have given the different group of molecules here. We have to tell that which is the least resonance stabilized. Options are, first one is benzene, then this oxygen directly connected to this alkene group, cyclic alkene group, and then this nitrogen directly connected to the benzene ring, and this structure having oxygen bond, double bond, and between this cycloalkene and these two chains are of methyl are connected to the carbon. So from these four options, you have to tell the least resonance stabilized structure. You have 10 seconds to think about this question. After that, we will see the answer. Okay, let's see. So the correct answer is option D, that is this structure. So aromatic compounds are stable due to the resonance, while non-aromatics are not. So aromatic compounds are those compounds in which, like benzene ring, okay, like we can arrange their double bonds alternatively too. Like we can write the benzene like this too, and we can shift this double bond here this double bond here, and this double bond here. This will also be called as benzene. That's why we form this circle in between of the benzene ring. Okay. So aromatic compounds, due to the resonance property, is most stable, while non-aromatic compounds are not. According to Huckel's rule or 4n+2 rule, both are same. Like Huckel rules are also known as 4n+2 rule. So according to this rule, for a planar or cyclic compound to be aromatic, its pi cloud must contain 4n+2 pi electrons. Okay, where n is any whole number 1, 2, 3, 4, 5, 6, 0. Okay, so what we are saying that according to Huckel's rule or 4n+2 rules, any planar or cyclic compound, if it have to be aromatic, its pi cloud must contain 4n+2 pi electrons. This total number of electron its pi cloud must have. There, this n is any whole number. Okay, so like suppose n is 0, so it will be 2 pi electrons. N is 1, it will be 6 pi electron. N is 2, it will be 10 pi electrons, right? So according to the Huckel rules, if any cyclic or planar structure is want to be or have to be aromatic, then their pi cloud must contain 4n+2 pi electrons, and n is the whole number. Thus, this 6 pi electron system, this 4 pi electron plus 2 electron system, and this which is 6 pi electron system, above given compounds are aromatic and stabilized by resonance due to the Huckel rule, because they follow the Huckel rule for n+2, right? They follow Huckel rules. But this compound given in the option D, this compound is non-aromatic because it does not follow the Huckel rule, hence least stabilized by the resonance, you can say. Because aromatic rings are more stabilized by resonance than the non-aromatics, right? Or if any cyclic or planar ring or structure wants to be aromatic, it should follow the Huckel rule 4n+2 pi rules, right? This compound will not show will not follow the Huckel rule. That's why it is non-aromatic, and that is why it is least stabilized by the resonance factor. And thus, our D option is the correct answer because we have asked about the least resonance stabilized structure. So D option, having this structure, is the correct answer, which is least resonance stabilized. Okay, now let's move on to the next question, question number 27. The addition of HCl to an alkene proceeds in 2 steps. So alkene are those structures in which double bond is present between 2 carbons, right? HCl is an acid. So we are adding HCl to the alkene, and it is happening in 2 steps. The first step is the attack of H positive ion to portion which can be shown as. So this is the question that HCl is, when we add HCl to the alkene, it will proceed in 2 steps. In the first step, the H positive ion attack will happen, but at which portion? So we have given some images of the attacking of H positive to the different carbons present in the alkene. You have to select the correct process. Option A is H positive ion is attacking to the first carbon of the double bond carbon, and then double bond is shifting to the second double bond carbon. Second, this double bond is shifting, the double bond charge or double bond electron is stabilizing the H positive. Third, H positive is at one side, but in the first process, this carbon will get stabilized, or this double bond will dissociate into the electrons to these 2 carbons, which is connected by the double bond. That means double bond is stabilizing these 2 carbons having double bond. Or all of these. You have to select the correct process, which happens in the first step of attacking of H positive on a portion of the alkene group. You have 10 seconds to think about this question. After that, we will see the answer. Let's see the answer. So the correct answer is option B. That is this. So first step in addition of HCl to the alkene proceeds as we have HCl, that means which produce HCl means it's positive and Cl negative. Okay. So basically this bond is this bond is going to break, giving us Cl negative and H positive, and then this double bond of C double bond C going to stabilize this H positive. That means the H is going to connect with this carbon here, and one carbon will become carbocation, and plus Cl negative we will get. After the first step, this is the process. First step process is this of addition of HCl to alkene, and thus our B option is the correct answer, which shows the correct step of attacking of H positive ion to the portion of the alkene. Okay, now let's move on to the next question. Question number 28. The most suitable method for separation of 1:1 mixture of ortho and para-nitrophenols is. Phenols, that means benzene ring having OH group attached to it. Nitrophenols means NO2 group is also attaching to the phenol group. Right? Phenol means benzene and OH, and somewhere NO2 is also attached to the benzene ring. And if we have given ortho and para, that means we have given the position at which nitro or NO2 group is attaching. So ortho means if you have a benzene ring and you start from 1, so 1 is para and 2 is ortho. Okay, so ortho and para nitrophenols mixture we have 1:1 mixture. What is the method we use to separate this 1:1 mixture of ortho and para nitrophenols? Options are sublimation, chromatography, crystallization, or stream distillation. You have 10 seconds to think about this question. After that, we will see the answer. Okay, let's see the answer. So the correct answer is option D, that is steam distillation. So orthonitrophenol exists as monomer because of chelation and hence steam volatile. So the orthonitrophenol exists as a monomer, and that means orthonitrophenol exists as a monomer means it can be combined with the another molecule to get a higher molecule. Okay, so it exists as a monomer, and because of chelation it exists as a monomer, and hence steam volatile. That's why it is steam volatile. Steam volatile means it can be converted to the steam easily. Thus, steam distillation method is used for the separation of 1:1 mixture of ortho and para nitrophenols. Okay, because the orthonitrophenol is steam volatile. It can be easily converted to the steam. It is the property of orthonitrophenol, and that is why we use the steam distillation process or steam distillation method for the separation of 1:1 mixture of ortho and para nitrophenols. Thus, D option is the correct answer. Thank you.